So welcome to week 7, University of Cincinnati Graduate Statistics course. So we finished last video talking about the trade-off that we should try to get between accuracy and precision. And we gave the example of this weather forecast that will tell us in the morning that, today the temperature can be anywhere between -20 and 110 Fahrenheit, which, it's accurate. The likelihood of the true temperature being between these two extremes is pretty much 100%. But we're losing precision. We basically don't know what to do. Which clothes are you going to put? So it's not very useful if your margin of error is so large that you can barely make the decision that you need to make with that estimate, right? So can we get the best of both worlds? That is it possible to increase precision without sacrificing accuracy? And I already hinted to you that the answer to that is yes. But the important piece is I want to go slowly here and explain to you how that's possible. So here is our formula for the confidence interval. And, we can set our desired accuracy by setting the z-value to be one that embraces 95%, 99%, 90%. So you choose the level of precision. To guarantee that to get that level of precision, you will not need this very large interval. We need to think about how to play around with this number here. And the way we play around with this number, that is part of the margin of error, is to have this value here large, such that the quotient here, the ratio here, will not be that big, right? So by having a large sample size, I can reduce this piece, right? Increasing the precision without having to sacrifice accuracy that much, right? So the answer is yes. And the how is to increase sample size. And why that strategy works? Because of what I just said, because increasing sample size reduces the standard error, which is the standard deviation divided by sample size, which reduces the full margin of error and improves precision without sacrificing the level of confidence or accuracy that you define, that you will fix by using the appropriate z, right? All right, let's check if you got this. Oh my gosh, I'll get out of the way when I can here. The General Social Survey is a sociological survey used to collect data on demographic characteristics and attitudes of residents of the United States. In 2010, the survey collected responses from 1,154 U.S. residents. Based on the survey results, 95% confidence interval for the average number of hours Americans have to relax or pursue activities that they enjoy after an average workday was found to be 3.53 to 3.83 hours. So here's what we wanted to know. How long Americans typically relax during the day, right? The survey did not ask every single resident. They just asked a sample, but they wanted to make an inference about the resting patterns of all Americans, right? So this is an inference they're making about the population by computing the confidence interval with a 95% confidence level, right? Let's see which of these statements is true or false. 95% of Americans spend 3.53 to 3.83 hours relaxing after a workday. Is that true? No, that's not what confidence intervals are, right? Confidence intervals is an estimate of the mean time of the typical time Americans spend relaxing, all Americans, right? What's the average? Well, the average is somewhere between 3.53 and 3.83. It's not about 95% Americans spending that amount of time relaxing, right? 95% of random samples of 1,000 154 Americans, will yield confidence intervals that contain the true average number of hours Americans spend relaxing after a workday. Now that's a definition of confidence interval, right? If I cast my net 100 times to grab the average time Americans spend relaxing, my net will have boundaries, will have a side, a width that will grab the true average 95% of the times, right? So it's not about 95% of Americans sleeping between these two numbers. It's about the mean being between these numbers 95% of the times. 95% of the time, the true average number of hours Americans spend relaxing after a workday is between this number and this number. Again, this is not true, right? The true average is fixed. It is what it is. It doesn't change. The true average in the population does not change every time I sample. What changes every time I sample is the size of my net, right? The size of my net will change every time. And if I compute that size 100 times, 95% of the times, it will include the true average. So that's why I like this drawing here. Oops. Because it shows us that the average in the population is fixed. But if I keep computing the interval every time, you note that the interval will have slightly different boundaries every time, right? The mean will be different every time I get a sample. The boundaries of the interval will be different every time when I get a sample. But it will include the true mean that does not change 95% of the time. That's what a confidence interval really is. So this here is not true. Then number D, we are 95% confident that Americans in this sample spend on average between this and this hours relaxing after a workday. That's true. So this, sorry, I should have said this is true, and this is true as well. All right. Now, the general survey asks, for how many days during the past 30 days was your mental health, which includes stress, depression, and problems with emotions, not good? Based on responses from 1,151 US residents, the survey reported a 95% confidence interval of 3.40 to 4.24 days in 2010. Let's interpret this interval in the context of this data. We are 95% confident that Americans on average have 3.4 to 4.24 bad mental health days per month. Suppose the researchers think a 99% confidence interval would be more appropriate for this interval. Will this new interval be narrower or wider than the 95% confidence interval? You should know that as confidence limit increases, so does the width of the confidence interval. It goes wider, right? So it is wider. That's the answer. So if I computed a 95% confidence interval and it's this size, the 99 will be this size. One more. A sample of 50 college students were asked how many exclusive relationships they've been in so far. The students in this sample had an average of 3.2 exclusive relationships with a standard deviation of 1.74. So here's a point estimate of how many relationships each student has been in. In addition, the sample distribution was only slightly skewed to the right. So only slightly skewed, 50. Estimate the true average number of exclusive relationships based on this sample using a 95% confidence interval. I would ask you to kind of work through this problem along with me, and we'll have a chance to work through more problems in the lab. So step 1, we'll check if the problem meets the conditions to compute confidence interval. The sample is random and has a size of 50, which is less than 10% of all college students. So that gives me some level of confidence that the sample is independent. So that's one of the criteria, right? So we can assume that the number of exclusive relationships that one student in the sample has is sort of independent than the other. B, n is greater than 30, and the distribution is not so skewed, right? If the distribution was very skewed, still the n was going to be greater than 30, and I would say, okay, we can assume that the sampling distribution is normal. So we can assume that the sampling distribution of the average number of exclusive relationships from samples of size 50 will be nearly normal, right? So we can apply the central limit theorem. Now let's compute the interval. We know the sample size. We know the average of the population. At least we have an estimate of it through our sample. We know the standard deviation of the population because we're estimating it from our sample. And so we know the standard error, which is standard deviation divided by square root of n. And that would give us 1.74 divided by square root of 50, about 0.246. And the confidence interval is the mean, which we have, plus or minus the z that gives us 95% confidence, which by now you should be starting to memorize. That's 1.96. And the standard error is what we just computed here, 0.246. So here is the confidence interval that if we simplify, 3.2 plus or minus 0.48. So we would say that with 95% confidence, the number of exclusive relationships that college students have been in will vary between 2.72 and 3.68. So that's the interpretation right there. So that's what I have for video lectures today. We're going to work on the labs together this week as well, so that we can apply the central limit theorem now to some hypothesis testing, okay? So we'll do that both through the use of the confidence interval itself as a rough way of doing hypothesis testing, and we'll also use what we call the z-test for hypothesis testing. But we'll be introduced to that in the lab, and then we'll have a more formal introduction next week. All right? See you then. Bye-bye.